Okay, so welcome back. Today we're going to take a slightly different tack than how we've been going before. So the previous plot of how we were doing things was we did some experiment, or that is to say we took some samples from some population, and we used this sample to get some reasonable estimates of possible values of parameters that described a population. So that is to say, the kind of input from the process was we had some sort of a model, which involved, let's say, some probability density function, for example, f, which depended maybe on some parameter or parameters theta. And so from this we made some observations, or in other words, got some samples. And then we want to produce some estimates, some sorts of reasonable estimates for these parameters theta, right? So model, observations, get some estimates. So that was the procedure we were looking at before. Now, an important feature of this process is that we are starting with no prior information about these parameters theta. So, in some sense, we're starting with some information about the model, namely we have a particular form of our probability density function, but we have no prior knowledge or expectations, so to speak, about these parameters or this parameter theta. Okay. Now, of course, we did do a variation on this where we were looking at the Bayesian approach, in which we also modeled these parameters with probability functions. Okay, so this is where you kind of have some prior information that you're encoding in terms of some probability density, for example, for theta. But so today we're going to take a different kind of an approach, which is today the theme is going to be to decide if statements about our parameters are reasonable. Okay, so more formally, what we're going to discuss is the notion of tests of hypothesis. So how does this go? What's the flavor of this? So okay, so again, we're starting out with some unknown population, but now we have two competing assumptions about the population. So this is kind of the framework that we're starting from. We have so two hypotheses, if you will, about the population. So let's call them hypothesis 0 and hypothesis 1. And what we would like to do is decide which one is the better hypothesis. Okay, so typically these are assumptions about some parameter in the model, like there's some unknown parameter theta, and hypothesis 0 might be that theta is less than a half, and hypothesis 1 might be that it's more than a half, or maybe hypothesis 0 is that the value is 0.5, let's say, maybe it's like a probability, and maybe hypothesis 1 is that it's not 0.5, okay, for example. And what we would, so what we'd like to do is collect some samples, do our experiment, get our sample variables x1 through xn, and from the results decide on which hypothesis to keep and which to get rid of. Okay, so the basic the basic procedure. So of course we need some decision criteria. So what are we going to do? We're going to decide on a statistic, some random variable, which is a function of our observations, whose value will tell us which to choose. choose. to choose. 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 choose And of course, we'll also have to come up with some decision criteria that tells us which to choose. So a little bit more formally, a test of hypothesis is going to consist of the following bits of information. On the one hand, we have to have hypotheses, H0 and H1, about our population, which really is to say about the probability distribution that describes the population. So typically about some parameter theta. Okay. But a test of hypothesis is going to consist, well, we have to have the hypotheses, we have to have a statistic, theta hat, and a partition of the possible values of theta hat into two sets. We'll call them region 0 and region 1. So the idea is that whenever you measure the value for the statistic theta hat, it will have to lie in one of these two regions, R0 and R1. So part of the setup is that we partition the values into these two sets. Okay. And then when the observed value of our statistic lies in R1, then we say we accept, I'll say R0, let's say, then we accept hypothesis 0 and we reject hypothesis 1. If theta is in R1, then we accept hypothesis 1 and we reject hypothesis 0. Okay? And this is the basic deal. So in practice, somebody gives, in practice, we start with these hypotheses we want to test. We try to find some statistic that will help us distinguish which hypothesis should be the one that we believe and which one we reject. And then we decide on two regions, which will tell us when the result will tell us to accept one and not the other. Now, I should say that, the way I've said it here, there's really like a symmetry between H0 and H1. They're kind of like, there's nothing in this definition that says you could have swapped H0 and H1. They're just symmetric. They're just two really placeholders, 0 and 1. In fact, life is not so symmetric typically. And in principle, the problems are really not symmetric about these hypotheses. So in practice, we generally have one hypothesis which represents some important actionable conclusion, and one hypothesis which means like we don't do anything, there's no action, no result, nothing out of the ordinary, so to speak. And these hypotheses are treated kind of differently. So in practice, this hypothesis H0, which we think of as don't do anything, no actionable result, or default, or whatever, is called the null hypothesis. And hypothesis H1, which means, actionable result, we just got something, we should be doing something, etc., is the alternative hypothesis. So, an important idea is that we don't want to call for action if there's no action to be called for, So we don't want to say, oh, there's an important result if there isn't one. So we don't want to conclude H1 is true when it isn't. So we want to kind of play it safe and conclude H0 unless we're really pretty sure that H0 is false. We want to, only think H1 if it's pretty darn likely that it's really H1. We don't want to accidentally say H1 when it's not true. Okay, so definition, a type 1 error is when the test tells us to conclude H1 when H0 is actually true. Okay. Okay, so this is what we don't want to do. Now, of course, implicitly, we're imagining that either H1 is true or H not is true. Really, so, there's this implicit assumption in how we discuss this that H1, exclusive or H0 is true. One or the other and not both. And this is just a kind of this is a human assumption that we're putting into this. It's not a formal logical thing. It's just the way we're setting it up and discussing it. Okay. So this is one important idea. We really don't want to conclude that H1 is true when it isn't. Of course, if H1 is true, we would like to know that it's true, because if there's some actionable thing that we should be doing, we really want to know that it's okay to do that as much as we can, reasonably. So definition, a type 2 error is when we reject H1 even though it's true. Okay, so I guess I should have mentioned for a type 1 error, the probability of a type 1 error has a special name. It's called alpha. So alpha is defined to be the probability of a type 1 error when you do your test. And if you have a small alpha, then that means that that when you get a positive result, it's probably for real, right? So alpha is called the level of significance of the test. Okay, so okay, and similarly, the type 2 errors. So what's the deal if if you make a type 2 error, then you should have had an actionable result, but you didn't. Your ability to find when this thing that you're looking for is actually true is it's some we call that the power of the test, like how likely it is to actually figure out your result is true when you're looking for it, and the chance that you don't do that is the type 2 error. So beta is the symbol we use to describe the probability of a type 2 error, and 1 minus beta, the probability that you found the result when there was a result to find, is called the power of the test. Okay. All right. So, I mean, as a general strategy, what are we going to try to do? We kind of alpha generally takes the first precedence. We usually want to make sure that we don't accidentally say something significant is true when it's not. And so we typically do our strategy. Our typical strategy is we fix some level for alpha. Maybe alpha is 0.5, or maybe it's 0.005 or whatever. We fix some level, And then we try to make beta as small as possible with this constraint on alpha. So we see how much power the test can have and still be that certain that we won't accidentally, get a false positive result.